So, very good afternoon to one and all. I would request all the participants to put their numbers in the chat box. सभी लोग मैनुअल अटेंडेंस नहीं लेते हुए, हमारे पास में अभी इतना टाइम नहीं, तो हम लोग आप क्या करिए, आपके चैट बॉक्स में नंबर डाल दीजिए प्लीज. All are requested to put their roll numbers in the chat box. So within a very short time, we will be joined by the Director, Board of Exam and Evaluation of our university, Professor B. N. Dole, sir. So just within a minute, we will join by him.
Your screen. काय करायचं? अच्छा.
So, very good afternoon to one and all. On behalf of UGC Malviya Mission Teachers Training Center, Dr. Babasaheb Ambedkar, Marathwada University, Chhatrapati Sambhaji Nagar, I welcome today's resource person, Director, Board of Exam and Evaluation of our university, Professor Dr. B.N. Dole, sir, to this afternoon session. Indeed, it is really an honor and pleasure to have Dr. B.N. Dole, sir, here as a resource person. A person with a vast teaching and research experience is here. He has also headed a department of physics of our university, has a vast teaching research experience, has been honored by several awards, fellowship in his academic career. He has also been awarded as the Ideal Teacher Award way back in the year 2015 by Dr. Babasaheb Ambedkar, Marathwada University, Chhatrapati Sambhaji Nagar. Also, he is a life member of Material Research Society of India, then life membership of Marathwada Janta Vikas Parishad, then Indian Association of Physics Teacher, then Physics Society of India, Indian Physics Association. Also, he has been awarded an Excellent Teacher Award way back in the year 2013. Then Rashtriya Gaurav Award in New Delhi he has got in 2010. His top 25 hottest article across the world ranked 22, capped 2011 in April-June 2011 issue. He also have been a collaboration with CMET, Chirlapalli, Hyderabad, Tata Institute of Fundamental Research, Kolaba, Mumbai, then Inter-University Accelerator Center, New Delhi. Also, UGC DA CSR Ahilya Devi Campus, Indore. Also, UGC DA CSR Park, Mumbai. As a teaching experience, he has started his journey as a research assistant and has continued as a professor in Department of Physics of our university. Also an administrative experience as a head of the department, then in charge for condensed material physics laboratory of Department of Physics of our university. Also, he was the in charge for library of Department of Physics. He has also been a warden for the boys hostel of our university, program officer of NSS PG unit of our university. Also, he has headed the Department of Electronics of our university and the Department of RUSA of our university. Under his able guidance, several students have awarded PhD, and also he has completed around 6 major research projects with an outlay of lakhs of rupees. Also, he has memorandum of understanding with Dr. Sathos Ilias, Department of Electrical Engineering Technology, Educational Institute of Western Greece since October 2018, and also with Dr. A. Branov, Moscow University, Moscow. He has a specialization in renewable energy, photovoltaic cell. Also, he has been the member of several committees in our university and has been the reviewer of well-reputed national and international journals. He has chaired many well-established conferences and workshops like International Conference of Nanoscience and Nanotechnology at Coimbatore Institute of Technology. Also, he has been conveyor and coordinator for many academic activities, board of examiner, a paper setter of various universities in Maharashtra and across India. Also, he has written and penned many national and international articles in journals as well as in the newspapers. Also, he has around 59 peer-reviewed publication. Also, he has 8 national level and 59 national international level publication with a total publication of 123. So indeed, it is really a pleasure and honor for all of us to have him here as a resource person. So again, on behalf of this entire group, I welcome Professor B.N. Dole, sir, and I would now hand over the session to him. Over to you, sir.
Thank you, Rafi sir. Am I audible?
Yes, sir, you are audible.
Okay. Say the Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar, and this EMMTTC center has organized this talk. And yeah. Okay. Hmm. The director of this center, Professor and Deans, Dhanasri Madam, Dhanasri Mahajan Madam, and the staff of this academic, this center, teaching and non-teaching, and the my friend Professor Rafe also, and the participants who join on online mode for this talk, the advanced materials for futuristic applications, innovations and opportunities. So this is the my talk, and I will share my views and ideas. So there would be the interaction with the participants who joined for this session on online mode. As you know that the material, and today the people are thinking about not only the material but the advanced materials. Advanced materials, when one can say this is the advanced material, yeah, this material is not advanced material. The material means it has a shape, size, volume, these properties. मला हे सांगा की सर्वांना जर मी याच लँग्वेज मध्ये बोललो तो कम्फर्टेबल आहे का, की मला मिक्स करायचं मध्ये मध्ये मराठी, इंग्लिश, हिंदी, I can use? Can I use?
Mix, sir, because many participants are from out of Maharashtra.
Out
बहुत
of
सारे लोग
Maharashtra.
हाँ महाराष्ट्र से बाहर है.
Okay, then no problem. So you see here, as and most of from science stream or humanities and social sciences, the most of the participants
Mix है sir.
mix. Okay, no problem then. So this is the material, and material carries the shape, size, okay, volume. These are the quantities, but also it has a dimensions, length, okay, and mass. These are the fundamental quantities. But one can understand that the material and matter. Matter has the initially 3 states and then the 2 states. It means equal. The material has the 5 states. Okay, how many states? Material has 5 states. Number 1, solid. Number 2, liquid. Number 3, gases. And fourth one, can anybody tell me? If you have an answer, please raise the hand. Fifth state. Yes, participant 27. You are not audible. Okay. Fourth one is a plasma. And fifth one, do you know? Anybody? Okay. You see, if we are studying the material, if we are studying the physics, yeah, science in general, and in particular physics, then one must know the material has how many states. So the material has the 5 states, and which I said here, which I told here. Now you see, if you go step by step, the material, and you see the material has certain length and mass. Okay, and therefore in physics these quantities are called the fundamental or basic quantities, means material, and in the dimensions then we use L, M and T. yeah, MLT, okay, means material has time, means time constant is there, it has the length and it has the mass. Therefore, this term. But now we are thinking about the material not at this stage, but the state of the material, yeah, form of the material should be the advanced, means which are available. From the available materials, we have to think about this, the advance. And if we study now, you see, my today's talk mainly on the very important aspect, that is the nanomaterials, nanotechnology, or nanowires, or you must know the nanowires, yeah, thin films, nanowires, nanobelts, and supercapacitors. Okay, now this is very important aspect, and therefore I consider here. Okay, now you see the technology day by day. Why I took this topic? Why I want to elaborate this topic? Why I want to discuss and interact with you? Because the materials and the day by day, the technology changing drastically, and if the technology changes drastically, then the important aspect that whether it is viable and applicable and useful to the mankind, okay, that is also we have to think. And is it viable, it is applicable, useful, or again the affordable, we have to think regarding this one. Now see, the technology has significantly increased the demand for high performance materials. We have the material, but the that material does not show the good performance, high performance, then with superior properties, that is, as I mentioned, advanced materials including nanomaterials, functional composites, metamaterials, smart materials, then the revolutionizing the various industries from energy storage to biomedical applications. Okay, this is again means you see, the one thing is that the material, nanomaterial, then the next form is the in the form of wire, and then third form is the in a films, and fourth form is in the energy storage devices, and here it is considered. Then the materials show the unique mechanical, electrical, optical, chemical properties, and making them essential to next generation technologies. Okay, now you see the general technology, next generation technology means the initial form of the technology and next generation form of the technology, both are very important. But in which case, now you see the copper wire is being used for extrusion of the wires, but nowadays that technology will take place the next technology, and that is the more important. This presentation outlines and explores the latest innovations in advanced materials, and it is focused on emerging trends, fabrication techniques, and novel applications. This is again very important. Novel applications, okay? Fabrication, designing, and emerging new trends. Now see here, this technology highlight again the commercialization and industrial adoption opportunities, addressing scalability, cost effectiveness, and sustainability challenges. Key topics covered include materials, graphene, MGen, TMD for energy storage. Now you see this graphene, the key topics covered including this graphene, MGen, TMDS. For what purpose? Energy storage, photocatalysis, flexible electronics, and sensors. Okay. nano composites and hybrid materials for enhanced mechanical and thermal performance, metamaterials for photonics, electromagnetic wave manipulation, electromagnetic wave manipulation, and stealth applications, bio-inspire and smart materials for biomedical, self-healing and adaptive technologies, sustainability challenges and the role of advanced materials in achieving a brighter future. So this is very important again, as you see, bio-inspired and smart materials, bio-inspired and smart materials for biomedical applications and self-healing and adaptive technologies means our concern science, these materials are concerned with the science, and particularly in physics, which one? Electromagnetic wave manipulation, stealth application, hybrid materials for enhanced mechanical and thermal performance, energy storage, that is the challenge, and therefore the sustainability challenges and the role of advanced materials in achieving achieving a greater future, that is more impactful here, greater future of these materials. Why? You can. Okay. Greater future. You see here the zero material. If you go through if you understand that one, those are the from at least up to 12th standard science background participants. If you have that background, you can easily understand that even though in a 10th standard we people learn that the dot, okay, point, okay, it doesn't have the dimensions. Single point is there. Okay, if you take a chalk piece and draw on the blackboard, just put your chalk piece on the BB, okay, blackboard. That point is nothing but the dot, and it doesn't have the dimensions, and that is why it is a zero dimension. In geometry, we people learn that, and here you see that is here it is shown. You can see this is a quantum dot. You see here, even though the fullerenes, the holy wall, okay, such type of dots are there. This is the fullerene, and gold nanoparticles are also okay. See, these are the materials, nanomaterials, NEP materials, classification based on dimensionality. See here, this is the gold nanoparticle, this is this one, fullerenes and quantum dots. These are the zero dimensional. Then the one dimensional is the rods, okay, wires, one dimensional. It has, in case of the nano, wire is a one dimensional. Tubes, this is a tube, one dimensional. And these are the gold nanowires, polymeric nanofibers, okay. Carbon nanotubes, rods, okay. Tubes, wires, rods, these are the one dimensional. Thin films, plates, layer structures, carbon coated nanoplates, graphene sheet. This is a graphene sheet. This is a layer nanomaterials. Okay, means thin films, layered sheets, graphene sheet. This is a graphene sheet. Okay, this is a graphene sheet. Carbon coated nanoplates, plates, films, sheets. Okay, these are the two dimensions. Okay, means this is one dimension, this is another dimension. Third one is not there. Okay, one is there, two is there. And now bulk nanomaterials, polycrystals, okay, liposome, polycrystalline, these are, okay. Then the dendrimer, this polycrystalline, it has the three dimension, bulk nanomaterials, okay, three dimensions. See here, what are advanced materials? That is more important because my topic, yeah, the title of this talk is related to this advanced materials. And what are the advanced materials now? The advanced materials, this term is being referred to engineer the substances with superior properties to conventional materials, making them suitable for high performance applications with superior properties. What are the advanced materials? To engineer substances, we have to engineer, we have to fabricate, we have to design, we have to synthesis the substances. It means we have to engineer the substances, with high performance, with means with superior properties to, okay, high performance applications, means synthesis the substances, then study their properties, synthesis material, study their properties, and making them suitable. After studying the properties, you will come to that conclusion, yeah, this material is good and it shows the high performance. Therefore, to engineer the substances with superior properties, okay, to conventional materials and making them suitable for high performance applications across various fields. These materials exhibit exceptional characteristics such as high mechanical strength, electrical conductivity, exceptional characteristics, exhibit exceptional, these metals means advanced materials have the high mechanical strength, electrical conductivity, thermal stability, optical tunability, and chemical reactivity. Means electrical conductivity, high mechanical strength, thermal stability, optical tunability, and chemical reactivity. Means why we people used to say, yeah, why one can say this advanced materials means superior properties, means one has to engineer the material with a superior properties to conventional materials, making them suitable for high performance applications. Now, why these materials are called advanced materials? Because they have high mechanical strength, optical tunability, chemical reactivity, electrical conductivity, and thermal stability. Okay, why this? Okay. So those materials carry these properties, then one can say these are the advanced materials. Now include the most famous examples here: graphene, MGen, high entropy alloys, metal organic frameworks, perovskites, and bio-inspired materials. Their unique properties enable their use in energy storage, environmental remediation, biomedical applications, and next generation electronics. Okay. Means their use in their unique properties enable their use in energy storage, environmental remediation, biomedical applications, and next generation electronics. Emerging trends in advanced materials. Now you can go through this and see the more important point, that is two-dimensional materials, graphene, MGen, and transition metal tires. Okay. So high electrical thermal conductivity, mechanical strength, and high surface area. Applications of these materials is the energy storage, flexible electronics, sensors. Okay. The two-dimensional materials is the energy storage device, flexible electronics, and sensors. Nano composites and hybrid materials. Now, this is the second point, and you can go through this. You can easily understand. Now you see the nano composites and hybrid materials, combining nanomaterials with polymers, metals, or ceramics for tailored properties. Structural materials, coatings, these are now the two-dimensional for energy storage and sensors, flexible, and nano composites and hybrid materials for coatings and biomedical uses. Metamaterials engineered to manipulate electromagnetic waves, negative refractive index applications, photonics, cloaking, and wireless communication. Smart and bio-inspired materials, self-healing, shape memory, these materials, bio-inspired materials, shape memory, biometric materials inspired by nature, applications, variable technologies, robotics, and medical devices. Now, these are the smart materials and inspired materials can be used. Now, the class of the materials. Here, oxides, sulfides, selenides, tellurides, nitrides, carbides, borides, and phosphides. These are the classes of the materials. Yeah, material class. See here, oxide means titanium oxide, zinc oxide, copper oxide, molybdenum oxide, tetraoxide, trioxide, iron oxide, tin dioxide, okay, titanium dioxide. These are the oxides. Sulfides means molybdenum dioxide. Sorry, sulfides means molybdenum disulfide, tungsten disulfide, zinc sulfide, cadmium sulfide. Okay, so these are the sulfides. Sulfide is fixed. Okay, suffix means here fixed. Sulfide, lead sulfide, CuS, PbS, WS2, zinc S, CdS, selenides. Ac2 is fixed. Then other elements are just put before the selenide, and therefore this is the diselenide, zinc selenide, cadmium selenide, copper selenide, lead selenide. Only selenide is fixed. Tellurides similar that Te3, bismuth telluride, antimony telluride, molybdenum ditelluride, all these. Nitrides, then the nitrogen is fixed, and therefore gallium nitride, aluminum nitride, tin nitride, that is the titanium nitride, then the silicon nitride, zirconium nitride, carbides, TiC, SiC, borides, TiB2 means titanium diboride, zirconium diboride, phosphides, GAP means gallium phosphide, indium phosphide, zinc phosphide, iron phosphide, copper phosphide. Now, dimensionality, and that is the, as we studied, that means the dimension, zero dimension. Which material is there? Quantum dot, gold particles. See here, the zero dimensional material, cadmium selenide, lead sulfide, zinc oxide, fluorines, and metal nanoparticles, that is the gold, silver, platinum, and carbon dots. One dimensional, as I described that one, wires, belts, and carbon nanotubes, nanowires. Okay. And examples are, this is the titanium dioxide, cadmium sulfide, zinc oxide, silicon, gallium nitride. These are the nanowires and nanocarbon nanotubes, CNTs. Two-dimensional material, that is the graphene, MGen. So this is one-dimensional, this is two-dimensional, graphene, thin films, phosphorine, okay, thin films, and three-dimensional metal organic frameworks, covalent organic frameworks, okay. These are the bulk metals, means copper, gold, iron, aluminium, bulk metals. Metals with all three dimensions, extending in space, providing the structural integrity and diverse functionalities. Okay, here this is the case. Synthesis technique for zero-dimensional, one-dimensional, two-dimensional, three-dimensional materials, depending on the desired morphologies, size, and functional properties. Below, we explore these techniques using zinc oxide, titanium dioxide, titanium nitride, and graphene oxide as a specific example. Now, here are, means you see, dear participants, you are listening this talk. Yeah, I would like to interact, and I am more comfortable than the talk. If I interact with you, means my interaction is with the participants. And now you just think over this. The zero-dimensional material, one-dimensional, two-dimensional, three-dimensional materials, we have to synthesis. And what are the synthesis routes? Here, 9 routes are outlined. 9 routes are here. Synthesis routes for the nanomaterials. And number 1 is the co-precipitation, CBD, chemical bath, successive ionic layer adsorption and reaction. Successive ionic layer adsorption, layer adsorption. So this adsorption and reaction, successive ionic layer adsorption and reaction. Soldier Okay, chemical vapor deposition, electrochemical deposition, ECD, electrochemical deposition, electrophoretic deposition, EPD, electrochemical deposition, CVD, chemical vapor deposition, Sol-Gel method, SILAR, CBD, CPM, co-precipitation method, CPM, EPD, electrophoretic deposition, Hammer's method, and hydrothermal method. Means there are the 9 techniques. Using any one, you can synthesize. One by one now. Here the chemicals are given and required chemicals and synthesis. Means whole procedure is outlined, elaborated, and that is as such. Co-precipitation, CPM method for 0 and 1 dimensional. That is, it involves the chemical precipitation of zinc 2 plus ions using precipitating agent NaOH, NH4OH. The reaction leads to the formation of zinc OH2, which decomposes into ZNO. Now, ZNO synthesis using co-precipitation method. This is co-precipitation of zinc 2 plus solution and NO3 twice in deionized water. Addition of precipitating agent, precipitating agent, that is NaOH, under stirring, formation of ZnOH2 precipitate, white precipitate forms, aging and washing. Now it settles, the precipitate, wash with ethanol and water, drying and calcination, heat at 400 to 600 degrees Celsius to obtain ZnO nanoparticles. This is the schematic diagram for the synthesis of co-precipitation method, for the synthesis of dots and wires. This is schematic. Now, second method is the CBD for 1 and 2. Okay. Example is the means titanium dioxide thin films, controlled chemical reaction in an aqueous solution forms a thin film on a substrate. Its flowchart is given. Preparation of solution, addition of complexing agents, dissolve titanium tetrachloride or titanium disulfate in water, and complexing agent to control pH, substrate immersion, deep glass for or FTO substrate deposition process, titanium dioxide nanoparticles nucleate and grow, annealing and characterization, heat at 450 degrees Celsius for phase conversion. This is the root. Here you see, this is the substrate, and which is the immersed in the solution. And now this reaction goes on here. SILAR, third one is the SILAR, that is the successive ionic layer adsorption and reaction. Okay. used for one-dimensional nanostructures. Example is titanium nitride. Okay. Example is titanium nitride. This is the schematic of Sol-Gel Sealer technique, sealer method. This is the Sol-Gel method used for zero-dimensional, one-dimensional, and two-dimensional materials. Example is titanium nitride oxide. Here, colloidal solution and its flowchart is titanium oxide synthesis using Sol-Gel method. Dissolution of titanium precursor, hydrolysis and condensation, add water and acid catalyst, gel formation, allow slow polymerization, aging and drying, remove solvent, calcination, heat at 500 degrees Celsius to crystallize TiO2. This is the chart here, titanium oxide nanoparticles. This is the step by step, and then we get the titanium oxide nanoparticles. CVD, chemical vapor deposition method, and it is also used for one-dimensional and two-dimensional synthesis of the materials. Titanium nitride nanoparticles, they are nanostructures now. Here the gas phase reactants deposit thin films or nanostructures on a substrate at high temperatures. Okay. So this is the flow chart for titanium nitride synthesis using chemical vapor deposition. Precursor gas introduction. Titanium tetrachloride and NH3 gases flow into chamber. Now reaction at high temperature. So 600 to 800 degrees Celsius in a vacuum. Titanium nitride deposition on substrate. Reaction produces titanium nitride thin film. Post-treatment and characterization. XRD same for structure analysis. Now EPD, that is the ECD, electrochemical deposition method, and it is used for one and two dimensional thin films, means two-dimensional films and one-dimensional nanowires. Titanium oxide electrodes. So uses this electrochemical reduction or oxidation to deposit titanium dioxide from a solution. Flow chart is given here. Preparation of electrolyte solution. Titanium tetrachloride in ethanol water mix. Electrode deposition on cathode. Okay, here electrolyte, cathode. Okay, it is here. Now this is the case here. Rinsing and drying, remove excess electrolyte, heat treatment, improve crystallinity at 400 degrees Celsius. This is the method, means electrochemical method here, electrochemical deposition method. See here the deposition, the material electrode deposition on cathode. So electrode is taken of this titanium oxide nanoparticles from under voltage. And this method, cathode, okay, and electrolyte solution. This is the cathode, this is the anode, voltage is applied. And here is the ethanol or titanium dioxide. Now the seventh one is the electrophoretic deposition, EPD method. As I mentioned, electrophoretic, ECD is the electrochemical, EPD is the electrophoretic. Here the best example is the graphene oxide thin film. Now the principle is the geocolloidal suspension is deposited under an electric field onto an electrode. Flow chart for geo deposition using EPD. Geo suspension preparation. Disperse geo in water or ethanol. Suspension preparation. Disperse geo in water or ethanol. Electrode setup. Use conductive substrates, that is the glass or FTO. Okay, material is there. Apply electric field. Geo moves towards the electrode. Deposition and drying. Remove solvent and anneal at 200 degrees Celsius. This is the nickel ions decorated geo. Okay. Here, see here, electrode setup. Use conductive substrates. Disperse geo in water or ethanol. Geo suspension. Apply electric field. Deposition and drying. Remove solvent and anneal at 200 degrees Celsius. Means geo suspension. Electrode setup. Here electrode. Cathode and anode. Okay. And apply the electric. Give the electric supply. Here is the titanium dioxide or ethanol. Electrolyte solution. Okay. Here this one. Now you see nickel ions decorated geo. This is the substrate. Hammer's method. The graphite is oxidized using KMnO4 and H2SO4. Exfoliated into a graphene oxide. Now the flowchart for this geosynthesis using Hammer's method. Graphite oxidation. Add KMnO4 to H2SO4. Graphite mix. Formation of geo. Stir at 50 degrees Celsius. Add H2O2 to stop reaction. Washing and centrifugation. Remove unreacted species. Drying and exfoliation. Okay, drying and exfoliation. Sonicate to obtain geo nanosheets. This is the method, and it's double distilled water here taken, and now this is the route, step by step. Hydrothermal method. This is the hydrothermal method used for 0D, 1D, 2D and 3D, means for all materials, special and advanced. Now the cobalt oxide quantum dots, zinc oxide nanowires, zinc sulfide nanowires, geo nanosheets, bismuth oxide nanosheets, manganese oxide nanoflex, and zinc sulfide nanospheres and nanocubes. So here, dear participants, you see These materials means the nanowires of these ZNO and ZNS we have synthesized, nanosheets also we have synthesized, manganese oxide nanoflakes also nanocubes, and ZNS zinc sulfide nanospheres and nanocubes also we synthesized in our Advanced Material Research Laboratory, Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar, very successfully. So for this, now the principle of this, I would like to just outline here. Uses high pressure and temperature in an autoclave to crystallize materials. Flow chart for zinc oxide, titanium dioxide synthesis using hydrothermal method. Preparation of precursors, zinc dinitride, okay, in aqueous solution. Transfer to autoclave. Heat at 180 to 250 degrees Celsius for 12 to 24 hours. Crystallization and growth. ZNO nanorods formation. Cooling, washing and drying. Purify product. Glucose stirring 20-minute transferring. Hydrothermal 160 degrees Celsius here. This is the stainless steel autoclave, means stainless steel Teflon coated autoclave. This is the, and then the solution here, this one transfer to this autoclave, then wash with deionized water and ethanol, then motor here, drying, and then calcination, then hollow ZNO nano wires. Here, this is the rices, okay, like this. This is glucose. Why hydrothermal method is employed here? Because it is given here the elaboration of the same, and that is widely regarded as an advanced and highly effective technique for synthesis, for synthesizing all dimensional materials, all dimensional nanomaterials, due to several key advantages over other synthesis methods, including sol-gel, co-precipitation, chemical CVD, PVD. Below are the reasons why the hydrothermal method is superior, because wide applicability for different nanostructures. Hydrothermal synthesis enables controlled nucleation and growth of nanorods, or quantum rod, controls the growth of nanorods or quantum dots. One-dimensional nanowires and nanotubes. One-dimensional nanowires, nanorods. Nanobelts. Okay. This method is highly applicable because the anisotropic growth in hydrothermal conditions allows the formation of well-aligned nanorods, nanowires, as I mentioned. Two-dimensional nanosheets, layered nanomaterials like graphene oxide, MOS2 and MGens can be synthesized with controlled thicknesses. Three-dimensional hierarchical structures, complex architectures like flower-like core shell and porous networks can be synthesized due to the self-assembly properties of hydrothermal reactions. precise morphology and size control. The temperature 1 to 300 degrees Celsius, pressure, reaction time, and precursor concentration can be precisely controlled, leading to highly quantum so here precise morphology, pressure, reaction time, and precursor concentration can be precisely controlled, leading to highly uniform and reproducible nanostructures. So, facilities the anisotropic growth of nanostructures, crucial for advanced material applications. This is crucial for advanced material applications. Eco-friendly and scalable. This method is eco-friendly, affordable, and scalable. Now it uses water or other green solvents, making it an environmentally friendly process compared to soldier, which may require toxic organic solvents. Or compared to other, this method doesn't allow to use the toxic but green substance solvents, which requires high vacuum and which is hazardous. The scalability is excellent, allowing large scale production of nanomaterials with low cost and high yield. High crystallinity and purity. High crystallinity and purity. Now here, what is the high crystallinity and purity of the material? We have to think about this. Hydrothermal process promotes defect-free crystal growth due to this low reaction kinetics, leading to highly crystalline structures. In addition to this, Sol-Gel and co-precipitation method often require post-annealing, which may introduce defects or impurities. Okay. Synthesis of complex and multi-component nanomaterials. It allows for doping, heterostructure formation, composite synthesis in single step. Now, for example, tungsten carbide based MnO2 nickel doped CO3O4 nanocomposites can be synthesized without multiple processing steps. The energy sufficient and low processing technique works at relatively low temperature. This technique works at relatively low temperature compared to CVD. Okay. Reduces energy consumption while still enabling high quality metal formation. High quality metal formation. Okay. Now, this is the case. Controlled surface chemistry. Okay. Controlled surface chemistry for functional applications. Controlled surface chemistry for functional applications here. Hydrothermal conditions allow for precise control over surface functionalization, which is very important for supercapacitors, enhanced charge storage, photocatalysis, membristors, and photosensitivity applications. Okay. Has prepared nanomaterials for the applications of photocatalytic, antibacterial, sensor, photodetector, and supercapacitor. Now, here is the actual work which I have done in our laboratory, and the material synthesized, that is the iron doped bismuth oxide nanoparticles, and the work was published in journal Results in Chemistry, Impact Factor is 2.3. These are the XRD, see here, these are the XRD graphs, peaks. Here is the sharpen the peak, the particle size is bigger. Smaller means wider, the particle size is sharpen means it goes, okay, means particle size reduces. If this bigger means you see sharpen, particle size is bigger. We will come to, you see. See here the crystallite size, it means plots in the graph, peaks are sharpened, then the size is the bigger. This is the crystallite size, 37 nanometer. See here, this is A, this, and here the width of this peak, here you see this, the width is very small, and then here the size wider little bit, wider than this, then see the size of the particle reduced. See here, means sharper the peak, bigger the sharper the peak, bigger the size, wider peak, smaller size. Okay, now see, this is the FE same field emission scanning electron microscope, and this is the particle size. Okay, here the micrographs of this one. This is the dopant percentage shown here. Photo degradation of methylene blue dye, pure and dope. See here, the methylene blue dye photo degradation. Here, this is for the 0 minute to 180 minute. Then this is the 0 again to 180 minute And these are the cycles here. Now you see degradation. Then the plot of time versus charge discharge capacitance. Plot of time log and variation of relative concentration of MB dye solution under visible light irradiation in the presence of pure nanorods over 5 cycles. Photocatalytic efficiency for pure bismuth oxide, then doped 3%, 0.3% iron, bismuth oxide, and all these. These are means efficiency. Photo degradation efficiency means photons degraded and calculated its efficiency and pseudo first order rate constant. Pseudo first order rate constant of pure and iron substituted bismuth oxide samples. So this is the antimicrobial activity of pure bismuth oxide and doped bismuth oxide, then the iron doped bismuth oxide for different concentrations against Bacillus bacteria and Aspergillus flavus fungi. Okay. Now you see here the area covered here and the area is covered here. This is 0.5% sample. Here you see the 0.5% iron doped bismuth oxide. The much more area is covered. That is the here 20. Here is 23. 20 millimeter means you see this area is covered. That is the 20 millimeter area. And here is 0.5. See this area. Using this Aspergillus flavus and this Bacillus bacteria. GO-based iron doped bismuth oxide. We have synthesized these materials in AMRL, Advanced Material Research Laboratory, Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar, and work published. This work has been published in Ceramic International with impact factor 5.1. Crystallographic study, you see here, this is a pure, and then you see here. Now, for pure, the peak, you see, the height is very small, but wider. Peak is not sharp that much. And here is the crystallite size is 17 point. Then sharpen, here is sharpen. Okay, here is little bit. Okay, see here. And we have calculated the microstrain and stacking faults also, volume and all these things. See here the efficient micrographs of the geodoped, not geo-based bismuth oxide, and 0.3, 0.5 and 0.7 iron doped bismuth oxide. Here is, these are the efficient, then the EDAX spectra of these materials, and it shows that the composition again. time evaluation spectra of Congo red azode degradation by pure bismuth oxide, geo and geo pure bismuth oxide, then doped, and these are the time evaluation spectra of Congo red azo degradation, azodi. Time versus this. It is shown here. All this the plot of time versus log this variation of these, and then for 3 cycles also it is given here. These are the again the plots for the same. Here the effects of various scavengers on the photocatalytic degradation efficiency. Okay. And this effect of various scavengers on the photocatalytic degradation efficiency. So here Congo red dye, this is CR dye, and this is the methyl orange, okay, and methylene blue mixed dye, okay. This is the efficiency calculated. Another material, geo based, as I mentioned, tin and iron co-doped bismuth oxide nanocomposites. And this work was published in Journal of Energy Storage. And you can see here its impact factor is nowadays it is 10. Okay, it is 10. You can see here. Now these are the peaks, and you can confirm that. You can calculate the here the crystallographic parameters and volume, then the crystalline size, then the stacking faults, okay, microstrain you can calculate using these peaks, and you can also calculate the crystallite size using the Debye formula, okay, and that is the Debye relation. You can see here the peak shape of peak is very sharp. It means the grain size is not sharp, not wider. Okay, here. Oh. Okay. Means wider the peak shape, wider the peak shape, grain size is small. Okay, grain size is small. Sharpen the peak, grain size is higher. Okay. Now these are the FSM of the selected system, and see here the sheets for this. Now these are the plots of the cyclic voltammetry curves of pure and doped. Okay, pure and doped samples at different scanning rates. Cyclic voltammetry, okay, for pure and doped. See the shape, that is the current density, okay, versus potential. This is the galvanostatic charge discharge curve, and see that one, galvanostatic charge discharge curve of all synthesized samples at 0.1 ampere per gram, and the calculated capacitance of all samples with different scan rates. Okay, this is the voltage and this is the time. Scan rate for this is charge transfer resistance 1.19. This is the 1.25. This is the 5 to 100 specific capacitance CS for pure. This is the higher 302 specific capacitance Faraday per gram solution resistance. Now this figure shows that the Nyquist plot and cyclic stability and Coulombic efficiency of synthesized samples. Okay, capacitance retention, Coulombic efficiency also cyclic number. Capacitance retention. See here the beautiful plot. We got here the Coulombic efficiency also. Now the titanium doped copper oxide nanoparticles, sorry, cobalt oxide. Okay. This work is also published in Materials Today Communication, and that is the 3.7 impact factor. This is the procedure is given. Here is the structural parameters, and here is that noise is observed. You can see the plots, and you see the lattice parameter and crystallite size is 21. Here, why it is noticed? Because microstrain and stacking fault. Field emission scanning electron microscopy. See here, very interesting results we got. And my dear participants, you go through these plots, yeah, these graphs, yeah, these images. Now you see, images are before you. See, very beautiful images. Field emission scanning electron microscope. These samples we prepared in the Advanced Materials Research Laboratory, Department of Physics, Dr. Babasaheb Ambedkar, Marathwada University, Chhatrapati Sambhajinagar. And see the images. These are the one-dimensional nanoparticles, means nanorods, nanowires. You can see here the nanorods. See, one-dimensional thickness of this TCO3. TCO3. This is third one, means C. This one, here you see. Photocatalytic activity, time study of the methylene blue degeneration spectra of samples of PCO, all these samples, and that is given here the plot of time versus CC0 capacitance. The degradation efficiency and pseudo first order rate constant of synthesized sample. This is the degradation efficiency, pseudo first order rate constant, and various reactive species also, the scavengers on the degradation. The another work is on geo-based titanium doped cobalt oxide nanocomposites, and this work has been published in Ceramic International. Okay. Now you see this is the work published in Ceramic International. Its impact factor is 5.1. See the structural parameters of as prepared sample, means structural parameters we have to calculate. This is the X-ray pattern, X-ray diffraction patterns. And see here, wider, not sharpen, but noise, too much noise is there. And for, you see here, this is wider, and then the crystallite size is a smaller. This is smaller than this. Okay, wider, crystallite size is smaller. This is wider, then little bit, then you see here is the sharp, wider, smaller, sharpen, greater, higher, see. Then the dislocation density per line also calculated, line per square meter, microstrain also, and here all parameters are equal. This is the, it carries cubic structure. See here, we got the sheets. Okay, sheets, images, AP same images of the synthesized GPCO, GTCO1 and GTCO3 samples. Length, GTCO1. Okay, GPCO and this one. Samples were calculated here. B. Photocatalytic activity. Now this is the photodegradation of MO, methyl orange and methylene blue mixed dye by these. And now this is the plot of time versus log. Recycles graph of samples. Effect of radical scavenger addition on auto degradation of MB and MO mixed dye under sunlight over GTCO1 nanocomposite calculated by UVVIS. The first order pseudo rate constant of photocatalytic efficiency of GPCO, GTCO1 and GTCO3 samples. See here, graphene oxide based nickel doped MnO2. Interesting. This work was published in Material Science in Semiconductor Processing. Its impact factor is 4.2. See here, the reference rod, then the working electrode, reference electrode, and counter electrode. These are the electrodes, okay? Shown here. This is the graphitic. Okay, this is AJ, and this is the reference, means the working rod. Okay. Delta MnO2 nickel doped. This is the RGO, means reduced graphene oxide. See here. This is nickel doped delta MnO2. See the AP same images. This is just flower like, a cotton like. See, we have synthesized these materials. See here, this is cyclic voltammetry. Okay, calculate the for different. This is the charge discharge curves of all samples at 1 ampere per gram with different times. The capacitance of all samples at different scan rates, electrochemical impedance spectroscopy of all nanocomposites. The specific capacitance of all as synthesized nanocomposite samples. Active electrode specific capacitance Faraday per gram at scan rate 10 milliamp volt per second. This is charge transfer resistance also calculated, and see here that charge transfer resistance enhanced. And that is the reduced graphene oxide iron doped alpha MnO2, and it is published in the Journal of Energy Storage. And as I said that its impact factor is this one, 9.4. See here the very interesting images we found, and that is like this nanowires. X-ray diffraction peaks of pattern of pure MnO2, RGO based pure and iron doped MnO2 nanocomposites, enlarged hue around the angle 26. These are the parameters. It means the lattice parameters and crystallized size, as I mentioned, sharpen, these bigger, wider, smaller. Pure, you see here, very sharper, sharper, see here, smaller, sharpen, pure, sharpen. Here is the wider. See here the plots, and here for C, geo-based iron doped MnO2 nanocomposites, wires, particle size and aspect ratio of all prepared samples. Cyclic voltagrams of PMO, GMO, GFMO, okay, all these samples. This is the galvanostatic charge discharge curve of all samples. At 5 ampere per gram current density. Okay. Plots of as prepared samples. Specific capacitance Faraday per gram at scan rate 10 millivolt per second. Charge transfer resistance So the time dependent absorption spectra of PMO, JMO, and GMFO, all these, and this is the time dependent absorption spectra. Now the plots of time versus C by C0 for all synthesized samples, recycle plots of all the above mentioned samples. The tungsten decorated reduced graphene oxide based iron nickel co-doped MnO2, published in the Journal of Material Science and Materials, and its impact factor is 9.4. Now you see this work, and you see here beautiful images of AFSM, and it is a like nanowires. You see the powder material we have taken here, the thin films we prepared and taken its AFSM images. See here, very small, but you see the beautiful picture of this TGO means this is the tungsten, okay? Tungsten decorated RGO. Here see alpha MnO2 plus cubic alpha Mn2O3 nanosphere. Here this is the iron and this is nickel, okay? Iron nickel doping. Tungsten GO based 3% iron nickel doped MnO2. See picture. This is the galvanostatic charge discharge curves. Now you can go through this. See the figure. This is the XRD fix. Okay. See the images again. Same images. And here is the nano wires formation of just the material shows its properties. Now this is the cyclic voltammetry. Okay. Cyclic voltammetry of TGO, MnO2, all these samples, and then the galvanostatic charge discharge. Okay. Means here the cycle we have to take. Then this is the capacitance retention. And this curve is the electrodes, electrochemical parameters of our synthesized samples, specific capacitance, solution resistance, and charge transfer resistance. And these are the nickel means nitrogen doped tungsten decorated GO-RGO. GO-RGO. This is GO-RGO, and this is nitrogen doped tungsten decorated GO-RGO now. Electrode system. Here is the working electrode. This is reference. This is counter electrode. There is supercapacitor functions here. This is the RGO. See this RGO means this is GO. This inside material is GO. Outside is this one RGO. Okay. Now you see this is TC and this is TGO RGO. Okay. And as I mentioned that TC sharpen the peak, smaller the crystallite size, wider the peak, bigger the, you see here, wider the peak, bigger the size. Yeah, bigger the width of the peak, sharpen the width of peak, and bigger the width of peak, crystallite size is bigger, and here smaller. Then other parameters also calculated, that is the microstrain, dislocation density, stacking force, U parameter, bond length, and C by A ratio. Shear sheets, AP same images of TC and TGO, RGO. Means this is the A, but here you see very sharp and beautiful sheets we observed, we noticed, and now this is the cyclic voltammetry of TC and TGO. You see the size of this one, potential, current density, current carrying density, and charge discharge curves of TC and this one for different. Now, this current density, specific capacitance, charge transfer resistance, and solution resistance of TC and TGO, RGO hybrid composite sample. Specific Faraday per gram, okay, capacitance, charge resistance, transfer, solution, and then resistance, all this. Electrochemical impedance spectroscopic plots of TC, TGO, RGO samples. Okay. Now these are the plots. Future scope of this work. Future scope of advanced nanomaterials. What is the future scope? Graphene functionalization and its applications. Okay. Now you see, we studied that the 2D nanomaterial with exceptional electrical, thermal, and mechanical properties, okay, is a key focus in cutting edge nanotechnology research. The functionalization of graphene by introducing heteroatoms, surface modifications, or hybrid structures, which enhances its applicability in various fields, including biomedical engineering, photo supercapacitors, solar cells, water purification. Below is the future scope of graphene functionalization in these domains. Okay. Now see here the graphene functionalization for biomedical engineering. This is one can use for the biomedical engineering. You can see here the graphene and its derivatives. Functionalized graphene, which shows biocompatibility, antibacterial properties, high specific area, excellent electrical conductivity, making them promising materials for biomedical applications. Means these materials, graphene and its derivatives. So, future scope, drug delivery. Functionalized graphene based nanocarriers can be used for targeted drug delivery and controlled release. So, graphene conjugated with polyethylene glycol or chitson can enhance biocompatibility, biosensors, and biodiagnostics. The graphene based electrochemical biosensors for real-time detection of diseases, that is cancer, diabetes, viruses, etc. DNA functionalized graphene for genetic sensing applications. So this is a graphene functionalization for biomedical engineering, graphene functionalization, antibacterial and antiviral coatings, tissue engineering and regenerative medicine, graphene based scaffolds for bone, neural and muscle regeneration due to their excellent mechanical strength and conductivity. Functionalized graphene coatings for biocompatible implants, orthopedic and dental implants, antibacterial and antiviral coatings, graphene oxide functionalized with silver, zinc oxide or copper for antimicrobial coatings in hospitals and medical devices. Graphene functionalization for photo supercapacitors. Graphene plays a crucial role in next generation energy storage due to high conductivity. Okay. Large surface area and excellent charge transport properties. Graphene plays a very vital role in next generation energy storage devices. Due to its high conductivity, large surface area, and excellent charge transport properties, functionalized graphene enhances the performance of photo supercapacitors by improving charge storage, stability, and light absorption. Future scope: graphene quantum dot hybrids for enhanced photo charging. Combining graphene with perovskite quantum dots or carbon dots can boost light absorption and charge separation. Okay. Quantum dots. Carbon dots can boost light absorption and charge separation. Combining graphene with perovskite quantum dots. Combining graphene with perovskite quantum dots or carbon dots can boost light absorption and charge separation. Graphene MGen composites for high performance electrodes. MGen and graphene hybrids can improve capacitive energy storage and cycling stability. Graphene based flexible and variable photo supercapacitors. Functionalized graphene can be integrated into flexible capacitor devices for variable electronics. Graphene as a transparent electrode for light absorption enhancement. Graphene, that is the transparent electrode for light absorption enhancement. So graphene functionalization for solar cells. Graphene is a it has high electrical conductivity, tunable work function, make it an ideal material for next generation photovoltaic devices. Graphene functionalization. Graphene has a high electrical resistivity, conductivity, and tunable work. Function make it an ideal material for next generation photovoltaic devices. Functionalization of graphene enhances electron mobility, charge separation, and light absorption, leading to a high efficiency solar cell. Future scope of the work, as I mentioned that one, graphene perovskite solar cells, that is PSC. Okay. PSC. Hello. Okay. These are the graphene quantum dots for light harvesting. Very interesting work and use. You see, the graphene quantum dots can be used as a sensitizer in dye sensitized solar cells. This material for improved efficiency. Graphene functionalization for water purification. Graphene-based nanomaterials offer excellent absorption, filtration, and antibacterial properties, making them ideal for advanced water purification technologies. Okay. Future scope. Graphene-based nanofiltration membranes. Functionalized graphene membranes with nanopores for efficient desalination and removal of heavy metals. Okay, these materials also can be used. Now the graphene enabled photocatalysis for wastewater treatment. Okay, this is the graphene enabled photocatalysis for wastewater treatment. Graphene TiO2 or graphene ZNO composites for degradation of organic pollutants using solar-driven photocatalysis. Graphene as an adsorbent for heavy metal removal. Functionalized graphene with carboxyl or hydroxyl groups for enhanced adsorption of lead, arsenic, and mercury. Antibacterial coating for water filters. Graphene based means geo-based antibacterial coatings for water filter. Graphene membranes functionalized with silver nanocomposites for bacterial inactivation in water filters, self-cleaning and anti-fouling graphene-based filters. See here the graphene membranes with super hydrophobic and antibacterial properties can prevent biofouling and enhance filtration longevity. So here these are the points which I covered. Now these are the future scope of the work which I covered. Now in addition to this, what we have done, that is before you, and here in our advanced material research laboratory successfully synthesized the nano ink from sugarcane bagasse. You see, this is the root and it is very cost effective, means affordable. What I used here for the synthesis of the nano ink, I will tell you. So, dear participants, hello. Just minute. Hello. See here, am I audible? Participants. Hello. Hello. Am I audible? You see, what I have done in laboratory, that is the Advanced Material Research Laboratory, Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar. See here, I procured the very cost-effective material. It is a costless material, sugarcane bagasse from the, as you know that the juice maker, sugarcane juice maker, they make the juice from the sugar. Then I contacted to that person and I said, please, means I require the 5 kg sugarcane bagasse. Can you tell me the cost? He said, there is no cost. How much quantity you require, you can take. Then I purchased one bag and then I took near about the 5 kg sugarcane bagasse. Then I processed that. What was in my mind? Because I want to synthesize the nano ink. And then I started the experiment because we know that at the in a sugarcane factory, plenty sugarcane bagasse is available, and it is useless because they use for the burning purposes. Okay, they prepare the good and all these things from that in that, and again the sugar using that. But as a burning material they use. But what is the use of that waste material? And it is to means waste and not useful. But I procured that sugarcane bagasse and then I processed, started the work in 19 February 2019 on that. That was the challenge because we have the plenty sugarcane bagasse, but it is useless waste material. Then I processed, started work, and then I got the nanoparticles from that. And I got the geo from that sugarcane bagasse from 5 kg. I got 500, that is 500 gram, means half kg. And then I processed and after that the synthesis technique I employed. Then what I done, the very means nanoparticles I reached up to that nanoparticle. Then the properties of that bulk material changed at nano level drastically. Then using that one, but there was also challenge before me. So dissolution, all the particles suspended at the top of the material. I was using the chemical, but this this material is means you can dissolve this material in H2SO4. But in my mind, we have to prepare the ink, and if we use the H2SO4, it is quite difficult. One cannot handle. There means you cannot handle. There will be the finger burning. Finger will be burned. Yeah, your hand. There will be the injury. So you cannot handle the chemical by your open hand. You cannot use. Okay, you cannot use that one by your hand, and we have to handle it every time. So then I thought it is quite difficult, because if this material is not dissolved, then there is the means how we can load into the paper. It is not possible. Then for that purpose, I was thinking day and night. After 9 months, I got this natural solution. And when I dissolve that material in a means naturally, then all the particles not suspended, not went to bottom, not at the top, but they dissolved completely. And I surprised, after the 9 months, I got that result. In means I started this experiment in 2019. Then in 2020, I got the completely dissolved solution. Then again, there was not, this was the first challenge, but the next challenge, when I loaded that material in the pen, there was the means in which pen, means in fountain pen. And when I was using that one from this nib, can you see? Here is my pen. You see, this is my pen. Okay. And in this pen, if I use, then the ink was coming out, and by drop by drop, and it was on the paper. If I used to write this paper on the page like this, now you can see this one. I will show you, I will demonstrate. Okay. Now you see, there was this one, that challenge, because the viscosity, what is the physics behind it again? Because I used here the solid state reaction route. Solid state reaction route for synthesis of this nano ink. Okay. And now thereafter, because you see, I started that one, because again the density of the material, then the viscosity of the material, all these parameters one has to take into account and consider all these. And therefore again it was quite difficult. I maintain these parameters very very cautiously. Okay. And then, because it was in my mind, if I load the material in the pen, then the drop should not come out from the nib. and if I put the pen in my pocket, so the ink should not come out because due to the leakage. So using this pen, I started the experiment and I got the succeed. I succeed when in 2024. Then my some friends they approached to me because you prepared this one, and there was the article in Marathi newspaper, but the people said me no, you have to submit the patent because this is very innovative idea, and what you prepared that is fully chemical free material. Then I submitted, I I I wrote a draft and submitted to the patent authority attorney, and then I got the patent published in 28, means I submitted this patent to the attorney general, patent attorney general, and then this patent published in May 2024. Okay, I got the publication, then the granted patent. Okay, in June 2025. So on this very novel and very ideal material, very impactful material, means here I synthesize the geo in my laboratory and using that one. So I synthesize the nano ink. Now you see the what is the actual research, useful and applied research that is in my hand. Now you see this was very interesting work, and today also it is very interesting. Now you can see here, I will show you that material. Okay, so I want to show you 90 participants. And just a minute, this is the slide. You see in this slide, this is the experimental setup, very cheap. And then you see, I wrote that time some lines on this Foolscape paper. This is the A4 paper, and on that. Now you can see here, this is the case. Then I tried to prepare the same content, but just differ for the stamp. Okay, stamp. And this is the also I prepared that ink, and you can also see this is the stamp for the stamp purpose. Okay, stamp pad ink, and then I use that one and I wrote this one now. Thank you. So here you can see. Now you see here. Huh. Slideshow, this is the case. Now I want to with this now I'm grateful to director Professor Dhansri Mahajan madam, who has given the opportunity and to interact with the participants. I'm thankful to the madam, and I'm also grateful to Dr. Rafe sir, who is the deputy director of this MMTTC. He invited me and given this opportunity, and the non-teaching staff of this center, because they organized this setup and given this chance. Last but not least, all the participants, you heard, listen very patiently. I can think because you see this much time, because while talking it is not difficult, but while listening it is quite difficult. And anybody is talking continuously and we have to hear that one carefully, it is quite difficult. Now I'm also from my bottom of heart thankful to all the participants. You heard this one. Now if there is a Rafe sir, Rafe sir, over to you. If you have any query, you can ask. Now, as I demonstrated this one, because this is my, as I said, this is the pen, and using this pen means this is the ink which we synthesize successfully. That is the nano ink. Just a minute, I will show you. Just a minute. Yeah. सर नाही का जस्ट मिनिट ओके ओके एक मिनिट इकडे या ही स्क्रीन नाही नाही आपल्याला हे हे मोठं करायचं आहे हे हाईड करायचं आहे आता मला त्यांच्याशी थोडं आता आहे का नाही आता लेक्चर झालं फक्त एक डेमॉन्स्ट्रेशन करायचं होतं मला हा झालं हा तेच करायचं होतं पाणी द्या थोडस याच्यामध्ये कोणतं नाही पाणी पाहिजे मला थोडं see now all the participants now you see this is the plane of paper fully white A4 size, there is no line, and this is my pen which I shown you. Now you see the ink we prepared in the laboratory, that is loaded in the pen, that is nano ink. Now on this paper I will write, okay, MMTTC, okay, Dr. Baba Saheb Ambedkar, Marathwada University, Chhatrapati Sambhaji Nagar. See, is it readable? Hello. Dear participants, Hello. Am I audible? Hello. Am I audible?
Screen.
शेयर नहीं का हाँ?
Participants, now we have permitted you to unmute yourself. You can ask the questions.
No, you
Yes,
just
sir. Audible, sir.
am I audible?
Yes, sir. Yes,
Huh,
sir.
now
Yes,
you
sir.
see, as I mentioned
sir.
that one, because I want to demonstrate this research work. This is very innovative research work. What I have done in the
Yes, sir.
Advanced Material Research Laboratory, Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar. What I said, you see, means I show paper, blank paper, blank.
Blank paper.
Now you see, this is a blank paper. Can you see?
काहीच नाही दिसत स्क्रीनवर.
Yes, sir. Yes, sir.
You can see now, okay?
Yes, sir. We can see, sir.
Yeah, okay. Now you see,
Yes, sir.
this is a blank paper. Both sides of the paper is a blank, okay? Both sides of the paper are blank, okay? See. Now, what I said, this is my pen, means in this pen, the ink we prepare in the Advanced Material Research Laboratory, Department of Physics, Dr. Babasaheb Ambedkar Marathwada. That is, as I stated and I elaborated, from the sugarcane bagasse, okay? I talk regarding that one. Now, actual experiment I want to show you. Now see this, within a second, I will write some lines and the name of the MMTTC, Dr. Babasaheb Ambedkar Marathwada. Just a minute, I will show you. Now you see, this name, can you see now on the paper?
Yes, sir.
You can see now, you see. Okay?
Yes, sir.
Yes, sir. Yes, sir.
How many seconds?
Yes, sir.
Near about the 10 seconds. Within 10 seconds. Now, I will show you. Now see, the letters are not blurred. Okay? Not scattered. Now, I will drop the water on the paper. Okay? Now see, my dear participants, I drop the water on the paper. Okay? See,
Okay, sir.
but the letters are as it is. There is no scattering of the letters, ink as it is. And you can read that name which I wrote. Okay? Before dropping the water, I poured the water. Paper is under the water. Okay? But there is no scattering of the ink. Okay? Letters are as it is. Your record is as it is. Okay? Your record is not broken. Okay? Got it? Now this is the nano ink. It is prepared using the sugarcane bagasse in the, as I mentioned, in this university. This is the patented ink now. Okay? Thank you very much for listening my talk very patiently. Thank you.
Thank you, sir. Thank you.
Very nice, sir.
Thank you, sir. Thank
This
you.
is my one of the activity which I completed and I got the
Thank you, sir.
patent. Another one is there also because near about the 400 people. Okay, those are from the, and now you see this is purely nano research, nano work. But what I prepared the another material using this means my research route. Okay, I applied for the same research route, and I synthesize the one material, and that is useful for the joint pain. Okay, means the near about the 400 persons took that and applied for the joint pain, and that is the joint pain reliever. Okay, this is my one again, another one. And I got the another patent on the supercapacitor. Thank you, my dear participants. You listen me carefully. Thank you, thank you. And again, last but not least, because the deputy director, Dr. Rafe sir, also joined for this, and he has given the opportunity for this talk. I'm thankful to Dr. Rafe sir and director Professor Dhanasri Mahajan madam, because she invited me and given this opportunity, and non-teaching staff of this center. Thank you very much. Thank you very much. Over to you, Rafe sir.
Thank you, sir. So, on behalf of UGC Malviya Mission Teachers Training Center, and especially on behalf of Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhaji Nagar, my special thanks to Professor B.N. Dole sir, Director, Board of Exam and Evaluation of our university, for sparing his valuable time. Indeed, being a Director BOE, that is Controller of Examination of an university which has hundreds of affiliated colleges, is not an easy task to spare his valuable time. So, out of his tough schedule, Professor B.N. Dole sir has spared his valuable time. So, I'm really thankful to you, sir, on behalf of this entire group. And with the permission of respected Professor B.N. Dole sir, I declare that this today's session is over. Thank you.
Okay.